Hello, welcome to the presentation of the work Active Localization for Mobile Service Robots in Symmetrical and Open Environment. My name is Federico Andrade. I'm with the Facultad de Ingeniería, Universidad de la República, from Montevideo, Uruguay. The outline for this presentation is a brief introduction, the problem statement, active localization system overview, then the experiment results, and the conclusions. Well, improving localization will lead to more secure, robust, and efficient robots. For indoor areas like hospital, houses, where global localization systems do not perform correctly, there is still some room to improve with active robot localization. The research questions which active localization want to answer is where to go and where to sense in order to improve the localization. Well, the problem we are addressing in this work is a robot in an indoor environment. We want to solve short-term active localization on symmetrical and open areas. The initial position of the robot is known, so there is a position tracking problem, and there is a path which is given by the mission planner. The map is represented as a two-dimensional occupancy grid, and the robot we are working with is a differential drive equipped with a laser rangefinder with a field of view of 70 degrees and a distance perception of 8 meters, and this laser is fixed to the frame of the robot. I'm going to show first the intuitive idea from this algorithm. So when the red arrows, which are the particles, spread away because of the robot movement, we cluster the particles, and from each cluster we find a representative particle, which are the gold arrows, and these gold arrows are set in a common fixed frame. You can see that in the middle image. So there we build a compound map, which the map from each of the representative particles. So the black points in the grid map are the points where both representatives vote that are occupied. The more clear points are the points where both representatives vote that are free. And the gray are cells which one representative vote that is free and the other representative vote that is occupied, and that are the cells we are interested in, because we want the robot to sense these cells to gain information. So the wrong hypothesis or the wrong particles will disappear, and the system will keep the best localized ones. So in this compound map, the more close to the robot point is selected, and then the robot rotates to sense it. And in the last image you can see the robot after rotate 90 degrees to the right, and you can see how the upper cluster became smaller and the other one became more focused. So the system overview, you can see it in this image. The main component are the blue boxes. The first one has as input the particle cloud from Monte Carlo localization. Then in this node we cluster the particle cloud and find the representative, which are the output, and in the second node, in the blue one, which is in the upper right, we took as input the representative, and we generate this overlapping map, and in that map we find the candidate cell. So the output from this module is the candidate cell, and there is a last module which is down in the right, which takes this candidate cell and find the commands for send it to the move base, for move the robot and sense the cell we want to sense. We did some preliminary experiment and we found out that we can't build the compound map with all the particles because the time of processing that map increases dramatically. For example, with 1000 particles you have to wait 1 minute to have the compound map. Spectral cluster and K-means++ are proposed in this work because both have good performance finding clusters in this kind of formations. And all the cells in the compound map are within the range of the robot sensors. So only with rotational movement the robot can sense the cells which will discard more particles. So to end this section, I want to show you a flowchart of the system. So the robot is following a path which is given by the mission planner. Then if it can find at least 2 clusters, then publish the representative from each cluster, build the compound map. In the compound map, find the most informative cell, and then rotate the robot to sense that cell, and then continue following the mission. Well, we did experiment in simulation and real world. We evaluate ground truth and localization uncertainty. 4 agents were used: passive localization, which is Monte Carlo localization, active localization using the scan clustering algorithm, and then the active localization with K-means++ and the active localization with spectral clustering. With both are our proposal. 10 runs with each agent in each environment, both in simulation and real environment. We used Turtlebot 2. Everything was fully developed in ROS, and the particle cloud size was 2000. Well, these are the simulated scenarios. Here you can see the waypoints given by the path planner. In the first case, in the left case, we have the one here, and then go all the way down, and then back to the right, to the left, to the right again, and finally goes up. And in the other case, start in the upper right, go all the way down and up and down again, finally enter in the room and go outside. Well, in the first environment, in the office environment, the spectral clustering and K-means++ had a better performance than the other agents. In particular, K-means++ keeps the ground truth error smaller, less than 10 centimeters, and also keep the dispersion smaller than the other agents. And in the second environment, which is the symmetric one, both spectral clustering and K-means++ have the smaller ground truth error, and also keep the dispersion smaller than the other agents. This is a real scenario. Is the floor 0 of the Instituto de Computación. Here in the right you can see the waypoints followed by the robots, which are at first go to the left, and then go to the right, go up, go down in a diagonal, and then go up again. Also, you can think as the service robot is searching for some object or tidying the house. And then here only 4 experiments were done, only just for confirmation of the result. And here we can see again that in real experiment, spectral clustering and K-means with this strategy of building a compound map and sensing the point, keep the ground truth error in around 13 and 14 centimeters, and also keeps low the dispersion. So as conclusions, this work presents an active localization system for the position tracking problem. The system has been oriented toward managing indoor environments with open areas and symmetric spaces, which are the most problematic ones. This experiment showed that the developed system decreases both ground truth and pose uncertainty during the robot mission. And finally, we are working in an active SLAM algorithm, using this proposal as a front end from mapping algorithm.